Good morning, good afternoon, everyone. Thank you for joining us for today's webinar, SCADA MES Integration, How to Unify Automated and Manual Processes. Our speaker today is our head of product here at Pico, Steve Wishau. I will let Steve take it from here.
Thank you, Shayna. Hello, everyone. Looking forward to diving into this conversation today about how we can really walk through the benefits of letting two factory systems communicate. So before we get started, we wanted to hear from you all how we're currently connecting our operator and machine data as a group. When we talk about this, about 20% of you are manually collecting that operator machine data. This is that traditional pen and paper on that shop floor traveler approach. 30% are collecting that information separately, whether that's an operation at a assembly bench where that operator is doing that work, or that machine data is getting stored somewhere, or that automation equipment data is getting stored somewhere. Those are two separate sets that need to be connected, or they're operating independently. And the kind of third, about half of you are not currently collecting any of that operator machine data as part of the assembly process or material subtraction or some work being performed. So just kind of a high level of what we're going to be walking through today. And we want to make sure that we're aligned on what we're trying to accomplish. We're collecting information for both manual and machine-based processes, and machine can mean a monument machine that is a traditional piece of capital equipment. It can be a automation cell with a robot arm moving things around, or taking measurements, or doing some sort of work in an automated, repeatable way. It's also going to cover some of that connectivity between those two types of systems, how we want to utilize those SCADA type systems, and how utilizing an MES can enhance that information. We want to try to unify that data as much as possible for full traceability, but allow those systems to operate in tandem. So we're collecting that information as we go, and that information is tied together as needed for those production processes. So at a high level, where are we on the SCADA MES landscape side of the house? MES expands and extends the capabilities of that SCADA system. Folks that ignition, Kepware, PLC work systems are great. Those are good for eliminating that repeatable work. That information usually is logged in some kind of historian way. But for the folks that are utilizing automated systems on an assembly line where things are moving from station to station, unless you're building hundreds of cars a day at an assembly line, it's really challenging to get automation and machines in every step of the way. So we want to augment that operator that isn't being completely working as in an automation setting. These are folks that are moving the equipment. We want to unify those data sets together and complement those capabilities. So let's kind of walk through some of the highlights of how these systems compare. We talk about a core focus on SCADA systems like ignition, like Kepware, like PLC-driven systems. Those are great for machine automation and monitoring. When we talk about MES and augmenting that operator, we want to talk about error-proofing standard work and process compliance. That error-proofing is that no-fault forwarding approach of, I can't move on to the next step in the process until I've successfully completed everything or received appropriate buy-offs and permissions from folks that enable that. I want to establish that standard work as a repeatable set of instructions that everyone can follow to adhere to that process compliance and performance. This is especially relevant in those fixed process type settings. Think aerospace, think med device, think I've got a PPAP process for automotive. We want to make sure that we have a consistent, repeatable process. That SCADA system is great at that real-time data and control, and we want to complement that with that worker guidance with the end-to-end traceability. The operator actions are capturing everything an operator might do, from operating that equipment, setting it up, troubleshooting when things go wrong, but also using manual handheld scanners or hand tools that you can't automate. So we want to tie those two systems together. And that goes directly into the type of data that we're capturing, that we are receiving inputs and data from those IoT connected tools, devices that the operator is using. Again, these are handheld torque tools, barcode scanners, the things that aren't directly tied to a machine being on, doors being opened, alarms being run, those traceability logs that you might come in from that machine. We want to have that right next to that human being, writing things down on a piece of paper, doing visual inspections and capturing that digitally. The benefit of the operator augmentation for that manual assembly and that error proofing is that it's going to be that enhancement on power, right? How are we laying on top of the digital tools, not necessarily having to build out a custom application job, HMI screen for each of those types of operations that need to be a little bit more general and capture that flexibility required for operator interaction instead of just a repeatable machine doing the same thing over and over again. So when we're talking about capturing the human side, we want to make sure we're logging in who's working at that station. That can be via an RFID badge that folks use to get in the building. That can be a digit pin identifying their information, or some barcode, QR code, 1D, 2D barcode scan that identifies where they're working. That where they're working is what we want to identify as the station. Where is that work being performed? It can be a manual workbench with a pegboard, a shadow board with manual tools. It can be a station on an automated assembly line where we start capturing that information. That work being performed is called the process. That's the work instructions you see on the screen. That's step-by-step guidance, whether the operator needs the true step-by-step granularity or not, or just needs to record the results, tying into the tools, barcode scanners that's being used at the station. We want to capture that information. When we do those inspections, and as simple as pass fails, where we're recording is something good, is something bad, or if we need to do some level of validation, whether that's taking a measurement with some calipers, using a tablet or a USB camera to take an image of something. How do we layer in all of that stuff, that inspection, that content that operator's capturing? Let's put that together as part of the content coming from those work instructions and augment that operator to capture that information. So what we'll be walking through is trying to eliminate those data silos. We have that information sitting on the machines. Historians are great, but you need to go in there, either query or look for timestamps of what we're doing. We want to make sure we can automate the operator being able to collect that information and utilize those tools. It helps contextualize that machine data. So when we are going down an assembly line and getting information from those machines and putting it with the operator, it's kind of contextualized in the context of, this is the thing I'm working on, here's the stations that we built it at, and here's the work that was being performed. And that really unlocks the next two things. One is that complete data set. I don't need to go into two different systems to look for this information. I can connect my manual station collection of efficiency numbers and manually recorded data with that full traceability of, here's the lot numbers, here's the expiration dates, here's all the timestamps of when this machine completed the work. And let's walk through, how do we connect this information from one system to the other to get that full build picture and not a partial over here, in a historian from SCADA, and worst case, a bunch of paper records that are, maybe scanned in for data retention purposes, but that information is not necessarily accessible because it's all just locked away on digital copies and not being ingested into a full system. So from here, we're going to dive into the product so we can kind of walk through, how do we start visualizing, conceptualizing, connecting this information as part of a process here. So I'm going to switch over to the Pico product here in general. The screen I have up is called our visual workflow, or our product workflow. The example we're going to be walking through is a battery pack assembly. This is your typical electric vehicle battery pack assembly, but it can be for industrial applications. This is that kind of overall structure of how we put that together. So there's kind of two lines that we want to take into account here. One, we have a battery module assembly line where we're loading in those batteries. We're taking all the other components to put that together, and we want to test that. From there, that goes into our pack line where we prep that enclosure. We take any number of assembled battery modules to go into this pack. Let's say that there's 10 modules within this pack. That is the higher charge rate that all get connected together. They get installed. Somebody comes over, puts in a bunch of harnesses and some manifolds to make sure the coolant is circulating appropriately. It's routed to where it wants to go, and of course, all those electrical connections between all the battery modules and the input-output of that fully assembled pack. From there, and we're going to be walking through the pack seal here as part of our automation example, how do we basically move this down the assembly line to make sure we're going from an operator manually sliding in these battery modules. They're going to manually connect a bunch of wires. And then we go over to our automation equipment of this pack seal process. How do we start tracking the information coming from that machine in addition to all these manual steps as part of that worker guidance? After that's done, of course, we can send it to the end of line for testing, but this is all going to be captured as part of our process here. So I'm going to jump into the pack seal process. We're starting from scratch just to show the kind of net start to finish here. So the first step in the process, we want to identify what are we working on. So this is the pack serial number scanning operation that we want to do to make sure that we are identifying the thing we're working on. That's that identifying feature, to be able to put that information together. We want to start the machine cycle to make sure all of our operating parameters are in place. So when this robot comes over and puts a bunch of adhesive on the pack for consistency, are we starting our process accordingly to our process and making sure all our parameters are good? And when we start recording that process, you want to make sure that we're using the right amount of epoxy, that we have that right dispense cycle in place. And when that's completed, we want to move that on to the next station. So as part of this kind of hybrid environment here, the first thing an operator is going to do is scan a barcode to identify this pack. So this pack is, again, one of those handheld barcode scanners. I want to record the information that is physically on that pack. This is just an epoxy dispensing robot. It doesn't have a barcode scanner on it, and it doesn't make sense to build that into the program. The ROI just isn't there. So we want that operator to identify what they're doing. So what we're going to just have them do is scan that barcode of that serial number that we're working on. We're going to identify it that this is the unique pack serial number. If we want to make sure we're scanning the right thing, that the serial number is a 5-digit number, for example, we can build in these patterns to help error-proof that operator, similar to what we talked about before, to ensure we're working on the right thing. I mentioned connecting those manual processes to that automation equipment. This pack seal, this epoxy is a very temperature sensitive, time sensitive operation that if I put a bunch of epoxy on these side panels and put it on my pack, I want to make sure that that pack is known good before I do this. It's a very time consuming rework operation to take those panels off. So before I want to put this in the equipment, I want to make sure those previous processes were complete, and I know I'm doing this dispense cycle on a known good pack. The way that we would do this without a connected MES SCADA layer is, a visual verification of an operator looking at the paperwork. Yep, my coworker down the line here has signed this off. Everything looks good. But if I pick up the wrong paperwork, it was pencil whipped inappropriately, there's something actually missing with it. I missed an NCR tag or some non-conformance information on this pack before I put it on the machine. That's where that rework starts to come in place, because we can't always properly communicate and things may fall through the cracks. So we're going to utilize features like this upstream process dependency, which allows us to say that as part of our process here, I can't start my pack seal operation until I know that all the harnesses and manifolds have been installed properly. So what this is functionally doing in the back end, when I start this process and scan the serial number, it's going to tell me I can't move forward if I don't have a valid completion for this harness and manifold install for the given serial number that I just scanned. So this very simple, identify what you're working on action at the part of your process is actually quite powerful before you start even triggering the start of the machine cycle. That we want to say, yes, this is the thing I'm working on. Yes, it's unique. I haven't done this before. It's not a duplicate serial number. And I want to make sure everything upstream at those manual stations is complete before I'm allowed to start my cycle. So this manual operation is, again, a very powerful tool for us to be able to capture this information at this station. The second piece of that is going to be making sure that this machine is able to be started. So let's say I'm at the start of my day here, and I want to make sure that the epoxy is at the right temperature before I start dispensing, because if it's not warm enough, it's going to come out all gloopy, and maybe there's no checks in the automation system that allows me to start this thing. If I'm an operator, I go press go, this machine's going to start for me. So instead of doing a scan or some other manual operator action, we're going to utilize this machine connection to start recording that information. So there's a couple different categories here before I build this out, just to walk through the options available. We can start a machine. So as an operator walking through the instructions, how do I trigger the start of a process from my work instructions if my HMI or that machine control panel is on, off, troubleshoot, error stop? How do I send a signal to that to say, yes, I'm a human being, I've done everything I need to do, let's start that machine. The second option is subscribing to a tag path or a machine aspect. So this is I need to talk to the machine and walk through, I need you to check a certain value for me, and I can't move forward until that value is either a true or a false, or in this case, which we're about to do, is making sure that epoxy temperature is at the right temperature before I can start that machine. The other two are, as you might expect, a little bit more straightforward. I want to read or write some information. That automation equipment or that machine has some specific data that I need to read. Go ahead and fetch that information for me, or I need to send it something. This is either triggering a binary state, true, false, 0, 1, or if that machine needs a specific input to do a calibration or adjustment. Let's say these packs that we're putting on from the battery might range in size from arbitrary numbers, 2 feet, 2.5 feet, 3 feet. I need to tell the machine what part number I'm working on, what size I'm working on, so the machine can use that as part of its homing mechanism or offsetting or calibrating itself before it starts the cycle, so it knows the right offset, the right information before it starts building. So let's go ahead and set up that epoxy example that I talked about before, where we need that temperature to be at the right value before we start working. So we're going to call this just a temp check. The machine that's catching that information, this example is ignition, but it doesn't necessarily matter to us whether it's ignition kepware coming straight from a PLC and we're using, an Allen Bradley complex logic library, a Modbus memory address. All of these are paths available as part of that server. So this ignition server has a number of IDs, and these are all configured as part of the device. It's just a big table of what are these tag paths, what are the specific path on that either PLC or OPC UA server that's being utilized as part of the ignition aspect here. It's the English plain language readable name that I can see a few different items here. But in this case, I want to pull that epoxy temperature value to make sure that as soon as I get to this step, I'm waiting for a specific value. So I'm not going to be able to complete this action, move to the next step in the instructions until this value reaches a threshold of 85 degrees. If it's colder than that, it's not going to dispense right. It's going to be too much, too little epoxy being dispensed, so this pack isn't going to accomplish its task. We can see that we can set it to true, false. We can set it to an upstream action value of, okay, let's do some math here. because, battery manufacturing it's sensitive to environmental controls. We know the temperature in the building because we have a thermocouple upstream. We want to make sure that epoxy is at least 20 degrees warmer than the ambient room temperature. We can set it to that and pick up a correct action value to support that. There's really no limit to the number of options here. We just want to make sure that we are waiting for that correct value. So let's say we're waiting for that, value of 85 degrees, and that's going to sit there and wait for that measurement to be successful. As soon as that completes, it'll automatically advance to the next part in the cycle where we can go back and say, I want to start this dispense cycle. So in this case, we're just going to select the right machine here to be able to walk through exactly what we want to accomplish here for the correct action and machine to be able to do this work. So this allows us to select that right equipment to be able to perform that action. From there, once that cycle starts, we can start recording that information. So when we go into that machine connection, we want to read that data. We want to see, the dispense volume that we completed. That robot knows how much epoxy it dispensed from the tank on the back. So we know that we're going to read the volume of that time. And I want as soon as we get to this step in the process and it's done, we can have the machine tell us, because we've successfully completed that step in the process, or an operator can come over and say, yep, I'm ready for this measurement now. To support this, we can also make sure our cycle time completes within that range. So we can start putting a min max on these measurements, because the machine's going to tell me, hey, I completed this cycle in 2 minutes and 30 seconds. If there's min maxes on that value, we can make sure we are receiving something. So if that error proofing isn't built into the automation directly, or it's challenging to do so, we can make sure those values that we're receiving are within an appropriate threshold before we collect the information that we want. So whether that's cycle time or a binary state of, there's a tag that we're subscribing to here that's a 1 or a 0 that's switching back and forth. We want to wait until it goes from a 0 to a 1 or a 1 or a 0. They'll advance that step. And at that point, it'll allow us to capture that dispense volume. We can certainly do that. So in this case, we want to capture that volume or mass of that information coming out. And I'm actually going to change it, my action label here, to be more accurate to what I'm recording, that we dispensed a certain number of mass of epoxy coming from that machine. We can put a min max on this as well. That'll reject that input, that it'll notify that operator of, oh, this wasn't appropriately dispensed. So maybe that tank was artificially, the machine thought it was full, but that sensor, that weight detection, realized that it dispensed too much, too little. We can put error proofing on that information coming from that machine as well. In this case, I'm just going to leave it blank. So this allows us to capture that information from this equipment, and when we go to the next step in the process, for example, this end of line test, we can make sure that, just like we did for pack seal, that end of line test, this is likely a very home built data acquisition system that's running some custom electrical testing that is disconnected from that robot dispensing that pack seal. We get that input of information to be able to capture it from that manual. Before we start this manual end of line test that runs a process at an electrical tester, we can confirm that automation cycle has been completed in the previous step in the process. I want to quickly touch on just what that configuration of those tags look like, so we can see, just like we have the manual equipment, whether that's pick-to-light bins or tablets or scanners or torque tools or label printers, we can configure that OPC server, in this case, ignition server, in the same way where we have a number of paths. We can have that plain language text with it, the number of addresses coming in from that system, the notes associated with it. If there's a specific function code we want, if there's a data type for filtering, that's all there too, and what stations that tag is available to be accessed from. All of this is here and configurable for us to manage and connect those processes from automated cells to both manual as well. So I'll switch back to our presentation here for us to wrap up. digital work instructions are free. We gave them away for free to be able to start capturing that manual work content of, here's my instructions, here's my worker guidance. From there, we can lay on those digital tools to be able to connect information. In this case, we're bringing in information from equipment, which is a connected station. For $100 a month for each one of those automated work cells, we can start connecting that information back to the high level information associated with all of the manual stations. So from next steps, you can sign up for digital work instructions online. We have a bunch of training resources, onboarding, self-help available as well as part of our training and onboarding series. And of course, you're always welcome to sign up for a demo to see how this stuff really works. And we can walk through your use cases together to make sure that we are covering all the bases needed. So I know we've got a few minutes left. I think now's a good time to maybe address some questions that came up throughout the process.
Yeah, Steve, we had a couple of questions come in, and if anyone else has any more questions right now, just go ahead and pop them into the Q&A. But our first one was, can you communicate to SCADA or PLCs over the local network?
Yeah, that's a good question. We actually encourage that. So that ignition server that I referenced is usually on a server rack or on a PC somewhere locally. All that needs to be configured is that local IP address and any security authentication to get there. If it's just a simple PLC, usually just an Ethernet connection there and an IP address, and with open firewall communication between Pico server deployment and that PLC or that ignition server, will allow that transaction to happen. There's no additional integration required. We essentially just need the authentication to get to that IP and be allowed to receive information from it. We've done all the integration work to configure that tag. Everything I walked through in the demo here is really the only additional configuration needed to access that information.
Okay, great. Thank you. One more that came in, one more question. Does Pico complement or replace the HMIs used on the equipment?
Yeah, another good question. The HMIs on the equipment can be challenging to support when you've got a big product mix, right? So most HMIs or operator interaction screens are start, stop, e-stop, as I mentioned, for troubleshooting. It's more machine status. Is it running? What are my most recent error codes? What's that information coming from that machine? And when we talk about that worker guidance, we want to augment what's available on the machine and set up those kind of instructions on what I'm supposed to do separate from the true machine operation itself. So while they can be used interchangeably, we want to make sure that that HMI is used for interacting and troubleshooting that machine, then augmenting the folks next to the machine doing extra work on top of that, right? We don't want you have to program a scanning operation into the HMI and a piece of automation equipment when we can collect that as part of the holistic view of the manufacturing line.
Okay, great. Just had another question come in asking if this would be available after the fact, if it's being recorded, and yes, it is. All of our webinars are available on our website, and you'll also receive an email with the link to the recording after the webinar. But we did have one more question, Steve. Can error states or false codes be captured in Pico from the equipment?
Absolutely. So that really goes in line with the kind of communication that I mentioned. If there's specific tags or paths that are tied to error states, those can be subscribed to. And if it's zero and it's false and there's no error codes, that's fine. But we can essentially connect to those machines and receive those codes as they're coming in, whether MT Connect or those faults coming from that machine. We can receive that information as part of the overall package. So when we were looking at how many times, if to use my battery example that we just went through, how many times has my robot faulted and dropped a battery that was being loaded into this machine, into my individual modules. Depending on how that machine is set up, we can receive those paths or faults through that same type of communication that we do for standard operating behavior. So for tracking that, whether it's a version of first pass yield or how your equipment's running, we want to make sure we're capturing and registering that information as necessary as well.
Great, thank you.
Okay, great. I think that brings us to time. I appreciate everybody's attendance today. As I mentioned here, we'd love to hear more from you about, next steps and where we want to go from here. All of these resources are available for you as well at picomes.com. So thank you, everyone. Appreciate it. And we'll see you next time.
Thank you, everyone. And just a reminder, a short survey will pop up when we're done. If you could please fill that out, and we will see you for our next webinar. Thank you.